waiting for a few more, so people might well join us. I'll just start and we'll get underway and hopefully we'll get some more as we go along. So good afternoon everybody, thank you for joining us. And this BCIA webinar with ABB, Liam Blackshaw, who you can see on the call there, will take attendees through an introduction into harmonics. For those that don't know me or the Building Controls Industry Association, because we've got a few new faces on, I'm Catherine, and the BCIA is the only UK trade association solely representing the building automation and controls and BEMS sector. Our 180 plus corporate members span all four corners of the United Kingdom and a supply side, so include manufacturers, systems integrators, specialist consultancies and distributors. A little bit of housekeeping before we get underway, if that's okay. So the webinar is being recorded, just so that you're aware of that, and it will be made available to BCIA member companies on our members platform. It will also be available on our YouTube channel, which is at BCIA_. Please can we ask you to keep yourself on mute and just turn your microphone on when invited to do so by the speakers, and cameras, if you like, can be left on or off, whatever your preference. There will be time for questions and answers during the session, and so we would ask you to pop any questions or comments you have in the chat. Alternatively, wait until the Q&A window is open and then use the raise hand function so that we can let people in. Our speaker today is Liam Blackshaw, as mentioned. He's the UK product manager for LV drives at ABB. So without further ado, I'm going to hand over to Liam now to get the webinar underway. So over to you, Liam.
That's fantastic. Thank you very much, Catherine, and good afternoon, everyone. And thank you for, definitely taking the time out during your lunch hour to look at this webinar about an introduction into harmonics, at least. Anyway, so hopefully you should be able to see that at least. And I'm going to just switch my camera off for now until the end, just to save on the bandwidth aspect at least. Anyway, so today is, as we said, it's all about an introduction into harmonics, the what, the causes, the effects, and the typical sort of means to mitigate harmonics on a typical system at least. Anyway, so I'll only quickly go through these because I know Catherine's already done the hard work initially. Obviously, it's myself, Liam Blackshaw, and I work at ABB as a UK product manager for our low voltage variable speed drives. But we also have on the call who will probably maybe add some comments to what I put to this is Chris Plum, and he is also working at ABB, our key account manager for our HVAC, our drives team at least. Anyway.
Hello all.
Perfect, thanks, Chris. So we've already touched on this, so the session is recorded, and any questions, what I would suggest is for now, please feel free to put them into the comment section, and then what we can do is we'll review those at the end anyway. Perfect. So let's now get to the main task at hand, and the talking points. What are harmonics, and how, and what are the effects of harmonics? What's the effects of harmonics? But we'll also look at things like the standards and the regulations that that users need to adhere to when they're looking at harmonics on a particular system. But we'll also look at the mitigation methods. How can I reduce or eliminate harmonics on my system? And then we'll sort of summarize towards the end by comparing those mitigation techniques and provide a little summary with with our Q&A at the end at least. Anyway. So it's now time to set the scene. What are harmonics? And just to start, just to literally set that scene, without heavily detailing that, is that, when we look at harmonics, it's essentially a power disturbance, where the power grid normally experiences huge variations of load, and they will react to changes in the voltage waveform. Causes of those power disturbances can be a number of things. It could range from things like electrical switching circuits to lightning. You can see on the right hand side of this slide set that there's different scenarios where we have things like voltage dips, power interruptions, things like transient overvoltages, could have things like voltage fluctuation, frequency fluctuation, where our frequency is slightly higher or lower than normal. But the one that we've obviously highlighted there is harmonic distortion. And harmonic distortions are what we class as repetitive but continuous deformations of the voltage or current waveform. All distortions, they result in deviations basically from that ideal sinusoidal waveform, which we put on this nice next slide nicely here. There we go, it's working now. So harmonic distortion. In an ideal supply network, ideally you want the voltage and the current waveforms to be sinusoidal, like the left-hand side of the slide here. We've touched on, there's a range of potential power quality issues exist, but ideally we want that that signal on the left-hand side, but in reality, it's very difficult to get that in a realistic situation. So we may end up something a little bit like what we see on the right-hand side. This is probably slightly over-exaggerated just to give you a bit of a feel and an understanding, but also an appreciation of what harmonics looks like. But that's what a typical waveform would look like, when you have a repetitive and predictable, non-sinusoidal voltage or current existing in your supply system. It means that the supply contains harmonic distortion. A little bit of history, about harmonics. As we said, that an electricity supply is hardly ever a pure sine wave where the voltage and the current are in phase with each other. We know that, in a lot of cases, the current will normally lag the voltage, resulting in power factor that's lower than your unity, 1. Voltage, normally distorted, and that, and what we can say is that voltage or current waveform can be analysed by what we call Fourier transformation. And this all comes back to a mathematician called Fourier, Joseph Fourier, who was a French mathematician back in 1700, and you can see his portrait on the right-hand side. And he developed the theory behind, how we could analyse waveforms using Fourier transformation. And what we look at is, when we look at that, we look at the overall distortion, and what we call that is the total harmonic distortion, THD. You may have seen it as THDI, which means total harmonic current distortion, or we change that I with a V, and it just means we're looking at the total harmonic voltage distortion. But both low power factor and harmonic distortion represent inefficiencies in the supply network. And I think what we'll do in the next couple of slides, well, there's a little bit of terminology that we'll go into, but I've hidden a lot of those slides just to because there's so much to talk about when we look at harmonics. We could spend hours on this. So when you get a copy of the slide set, the slides that are hidden will be shown, so you can get an idea of the different bits of terminology, at least anyway. So yeah, Fourier transformation is effectively a mathematical function to show different parts of a continuous signal. So when we look at Fourier transformation, for example, we look at, we don't particularly look at the waveform. We look at the harmonic components, which you can see on the right-hand side. We do what we call like a frequency spectrum analysis, where the first order, and don't worry if you forget any of these terms, because we'll probably touch on them later on, is our fundamental current or voltage, and then the multiples of that are our fundamentals, at least. Not the fundamentals, our harmonics, at least. So we always look at it as a percentage of that individually, but then we summarize that and do an RMS value to get our total harmonic distortion. So yeah, harmonics or EMC, quite an interesting aspect, at least, is that you've got and this is a key thing to say, is that harmonics are not EMC disturbances. Harmonic voltages, currents, are a low frequency phenomena, typically range between 100 hertz to 3 kilohertz. And it's, when we look at that, effectively harmonics do not mean the same thing as, radio frequency interference, where that spectrum is wide, covering a whole range of frequencies. And some of those frequencies are in the realm of harmonics, whereas others fall under the EMC directive. And they are not the same and have different solutions, of course, where harmonics is typically a low frequency relation to the supply side, and EMC is more to the high frequency side. So typically above 100 kilohertz ish, roughly, at least anyway. But yeah, typically harmonics are at low frequencies. There can be frequencies above maybe the 5 kilohertz threshold. But often people, and this is the key misconception, is that a lot of users are trying to reduce harmonics by using methods that decrease RFI disturbances. But of course, because of these frequencies are different, these methods do not address harmonics. And typically harmonics is more of a conductive phenomenon, while RFI disturbances can be both conductive and radiative as well. And obviously when I say EMC, we're looking at electromagnetic compatibility, and those kind of standards address both interference and harmonics to a certain extent. So as an example, we mentioned things like the order of things. So if we looked at a 50 hertz network, for example, and I wanted to look at the 5 kilohertz signal, that would be the 100th order, because it's or what we class as the 100th order, because it's 50 times 100, because it's 5 kilohertz. If we wanted to look at the 5th order of harmonics, we multiply those two together, and that gives us 250 hertz, and so forth and so forth. So when we look at the cause of harmonics, it is typically harmonics. The cause of it is nonlinear loads that draw a current in a periodic, non-sinusoidal or distorting manner. Always think about it is, or best way to think about it is of a diode opening or closing and its associated current, and how we're applying effectively an AC signal to a DC component. And the harmonics, or the harmonic content, is a mathematical concept that allows that quantification and the simplified analysis of nonlinear waveforms. We've probably touched, it's both present in network voltages and currents. But as a result of all this, is that it's the nonlinear current that the draw of that creates that nonlinear voltage as it flows through the electrical network. So effectively, when drawing current harmonics, as a result of that, you will get voltage harmonics. And harmonic currents cause inefficiencies and system losses. So things like cabling and transformers, when we may start to overload those. But the harmonic voltage aspect of it is what causes interference with other equipment as well. The main culprits, obviously variable speed drives. It could be EC fans, UPS systems, commercial equipment that has like a switch mode power supply in them. So things like computers, photocopiers, and fluorescent lighting. They're the key culprits, and it's always, and I'm going to probably sound biased because of my background, is that whenever we fit in or install a variable speed drive onto a system, it's always, it's the drive that's caused that. It could be to a certain aspect, but in some cases it could be what we call, it's the straw that broke the camel's back. It could be that little bit that we add to it that just sends it over to the thresholds and causes issues on the supply system. So it may not always be, it can be to blame, but it may not always be the culprit, at least anyway. And it's always understanding on what you've currently got on your distribution system, at least anyway. So yeah, source of harmonics, we've pretty much touched upon that at least anyway. So there's a few more examples there just to tell you it's basically anything that has some form of switching device on there, at least anyway. So a couple of examples of when we look at, distortion as an example, that the top one there is what you would see as the real signal. But if we were to break that down, you can see what it is, consisting of, at least, and that's the fundamental signal, which is our supply frequency at a given, interval, given magnitude, should say, and within that, the associated harmonic components over a given period. So in this example, we've got what we class as the first order, but also the fifth and seventh, and summating those together gives us our actual real signal, at least anyway. So you can see here, I'm just going to get my pointer now, for example. If we took it here, we're looking at, the peak value of our fundamental plus our minus, and our minus here. When we put that in line, we get that slight little dip there. So we're summating those signals at a given point, or all given points at least anyway. So as I said before, we never really, when we look at harmonics, look at sort of waveforms. Maybe do if we're doing a more detailed analysis to understand, if we're looking at a particular issue. But when we want to do a report, for example, we always look at what we call the frequency spectrum. And it's always worth looking at things like percentages, the percentage of the fundamental. When you look at this as an example, it's like, well, great. Well, what does that mean to me? Okay, it tells you a particular harmonic order, what level of current or voltage I'm getting. It could be in the milliamps, could be a lot less than that. But it's within having those standards or regulations that tells us that at a particular order, our harmonics on a particular part of the system need to be at this level given certain criteria. Which probably moves us on next nicely now to the effects of harmonics, the problems that are caused when we have harmonics on our system. So if we take the typical supply network, we've already touched on, current distortion is caused by nonlinear components, switching devices. Voltage distortion is something more at a system level. And by calculating that sort of voltage distortion, it requires knowing what the current distortion is, but also the system short circuit impedance as well. So we have the current and voltage distortion, which I've probably not the best way to highlight it, at least, but you can see the dashed lines to say where they typically reside within. But one thing we need to consider as well is things like background distortion as well. So things that are contributing from either the LV or HV side of the network depend on what we call what we class as the point of common coupling, PCC. And that means whenever we look at harmonics, and especially from a standards perspective, we always measure at the point of common coupling. And in layman's terms, what that means is we always measure at the point of where we're sharing our supply with another user. And that could be on the LV side, it could be on the HV side. It all depends on the user's network. So as a result of that, there must be, or some within their present, from neighbouring networks, there'll be some contribution from there. And what you should normally do is investigate the harmonic impact when the transformer is heavily loaded, or if the generator supply has a high impedance, at least anyway. So when we look at harmonics and the problems that are created from that, there's a couple of examples there just to name but a few, but also some images and nice pictures to go with that, where we have things like the overheating of components, the failure of protection devices, but also things like damaging sensitive electronics or equipment that's on that system. And that the harmonics will increase transformer losses and cause them to overheat over over a given period, over its, what its rated data is without being overloaded. This could be seen as things like, overheating of the windings, or it's often seen as uneven heating of the windings, at least, even though each phase is close to evenly loaded. Slight bit of a tongue twister there, at least, anyway. But harmonic currents, can often expedite the loosening of breaker connections at both line and load sides. So, if you've got a loose connection, it could make that condition worse, to a point where we're starting to overheat things, at least anyway, and causing failures. And this is the kind of things that it's due to the natural expansion, but also contraction that occurs that, as harmonic currents can increase and decrease with equipment use during certain times of the day. So things if they're switching on or off at a certain period. Those loose connections obviously will increase the junction temperatures and cause the breaker to trip on what it thought could be an excessive load, when in reality it was a loose connection. So transformers, the load noise is predominantly produced by axial and radial vibration of the windings, but higher even harmonics also appear in the resulting core vibration at higher induction levels, at least. And the key message is that, without addressing these harmonics, you could have a troublesome operation of your system, where as a result of that, you might have failures, breakdowns, so you have some form of downtime. You could also have some high running costs as well, because you have an inefficient system, and over the course of an equipment or system's life cycle, those life cycle costs may start to get high and increase, as well as maybe in some cases you could get penalised by the distributed network operator, the DNO. They could penalise you for having a high levels of harmonic content on your system. They may, they could, give you a penalty. They could, in some cases, have the right to cut off supply to your system, to name but a few things. But it's also worth noting as well, when we look at harmonics generator operation, if we've got a system that's, maybe has a backup generator on there, and it has high harmonic loads that are present, generating or operating generators with that high harmonic load present their own problems, where in some cases the generator must be able to handle that harmonic current, which will derate its capacity. Again, being biased, when we look at variable speed drives, we normally say, as a rule of thumb, you tend to derate that by about 50%. So if you're using a traditional sort of 6-pulse drive, if it was, let's say, 100 kilowatts, for example, you would rate your generator to be 200 kilowatts, and maybe slightly more if it was a transformer. So it's kind of looking at, instead of eliminating harmonics, it's kind of managing them, overcompensating for them. But in addition to that, if we're looking at older generators, for example, the voltage regulation system can become unstable with high harmonic loads. So it's always worth checking with the generator manufacturer for its use on harmonic loads, just to make sure that there's no tolerances that you have to adhere to, at least anyway. But when we look at power quality as well, harmonics always seems to be the bad person, and it does get blamed for many problems, where you might have things where it's reading crazy values, and this is all coming back to, is it EMC or is it harmonics? So it's always remembering that things like this may not necessarily always be harmonics, and are often not harmonics. It could be things like common mode voltage, again EMC, but it also could come down to the design or installation of the system. It might be poor, where things like fuse selection's not been done correctly, in terms of compatibility. It's you've got some old equipment on there that's not been it's not been adequately filtered. Things like your connections, your earth neutral link connections, have they been terminated properly? Is it a poor earthing design or installation? And things like earthing rings on flow meters, for example. But also the key thing as well is, how is that cable being routed? What type of cable has been selected. Is it a screen cable or is it not screened? Which is very apparent, or especially on borehole with submersible pumps, where ideally you need to have a screen cable, and in some cases when they become predefined, they may not have that screen cable, at least anyway. So yeah, standards and regulations are a very key topic, and who is responsible for that, at least anyway. And just to give you a bit of an overview, there are various guidelines, standards, engineering recommendations, and it all depends on when you're looking at the network. If you're looking at it from a utility level, you have the EN 50160, which is the system voltage requirements. I would say very rarely, for those on the call, you may not get involved in those as much. The ones you probably get involved in a lot is the second set, which is at the customer or system level. If we're looking at it from a UK perspective, we're looking at G55, which came into effect around about June 2020, so about just over 4 years ago, where the prominent changes on that were things like how we assess this, the various stages, and the extension of harmonic orders up to the 100th order as well. You also have, and this is more if you're a manufacturer, the product level kind of harmonics. So you've got the 61800s or the 61000s, depending on the loading of that piece of product, at least anyway. So the limits for harmonic distortion, they're always defined by national or international standards and recommendations. It's down to the DNO. They're responsible for ensuring the system voltage requirements are met at the utility level, but it's them to enforce it to the end user as well. So when we look at it from a system level, they need to enforce it to their end users to say you need to be within a certain level. And what they will always tend to do is say they need to meet G55, or in some cases, because you may not have the right kit or the necessary kit to measure that, they might just say we can adhere to the previous standard G54, for instance. And that probably ties us in nicely for G55, at least, is G55 is an engineering recommendation by the Engineering, I think it's Networks Association, the ENA, and this is the planning levels for harmonic voltage distortion and the connection of non-linear equipment to transmission systems and distribution networks in the UK. Although it's an engineering recommendation, it's still effectively an installation standard, and in effect a UK national standard, as it forms part of the grid code, at least. And this is a key thing. This is probably a key thing, is no single product or item of equipment can be said to meet G55. When we look at G55, we're looking at, it's all about the system. We're not looking at individual components or individual parts of the installation or the network. We're going back to where that point of common coupling is, the PCC. And that's where we measure our harmonic content. And that's where we say, depending on the stage or criteria, we say that's what limits we need to adhere to. If we're adding, let's say, something that has a low load, something that's less than or equal to 16 amps, there's normally in a lot of cases, and there's no need for an assessment. Technically, you can connect without any further action, and this is assuming you can meet what they class as the stage 1A requirements. But if it's greater than 16 or less than 75 amps, then you typically need to follow either stages 1B, C, or D. Stages 2 and 3, they're designed more for connections where the point of common coupling, so where you're measuring, are at levels that could be at below 33 kilovolts, or when you've gone through the criteria, it might be that you can't able to adhere to stage 1, so you move on to stage 2. And this process is kind of designed now so it's in a linear process, such that the assessments are applied in sub-stages, and the final one, which is stage 3, uses a proportionment of harmonic headroom to set the limits for each connection, outlining the minimum requirements for the harmonic specification at least. And just to give you a bit of an idea, so you have what we call tables in G55. So I've took this one through, for example, which is the planning and compatibility levels for harmonic voltages above 400 volts but less than 25 kilovolts, and this is what it would tell you, is that you want to plan. They have planning levels and compatibility levels, and what you always tend to do is always plan for the planning levels, try and aim for the planning levels, but you have got a little bit of leeway in that you need to meet the compatibility levels. And it's always maybe a silly analogy to think of is when you're firing an arrow with your bow and you're aiming for that target. You always aim for a bit higher, but it actually goes a bit lower at least anyway. So you aim for the planning levels, but you need to ensure you hit those compatibility levels definitely. So mitigation methods at least anyway. So just to give you a bit of an overview, there are various different ways of how we can mitigate harmonics on our system. There's several possible solutions. Some of them are not all or are as effective as others. Some of them, can in fact be very difficult to to use indeed. So things like passive filters, for example. The key thing is that it varies by installation or by the system, and depending on what you've got set up on there. And it's never a case of kind of a one size fits all. It could be that you might have a little bit of one part of mitigation mixed with another. Or it could be you might have one overall thing that covers the whole system. It always varies by system, definitely. Couple of things as well. I've put a couple of, again, related to drive things, but things that just to be aware of. And this one here is what we call multi-pulse systems, at least anyway, which was a means to cancel out harmonics on a system where it was a kind of an old traditional way of eliminating harmonics when you had a large power drive on a system where you would have either a 12 pulse and if it could be greater than 18 pulses, where you'd have a complex transformer system where it'd have multiple windings, secondary windings, sets of drive rectifiers, the DC link and capacitors, and you can see at the bottom that the more levels of rectification there was, you can see how the current distortion become less, at least anyway. So that's kind of one method, just to give you more of an awareness of this is probably, it's still out there, not in high quantities, but it's something to be aware of. But one that you may have seen quite often is things like passive filters, where you may have reactors and capacitors in series or parallel. Then we have one set per harmonic frequency that's filtered, but also offers a low impedance path for harmonic components. And the key thing is that the filtering efficiency depends on the network parameters. So, and this is the key, the key thing about that is that a lot of engineering's involved, or a certain level of engineering involved to get the right passive filter set up. And if those network parameters change over time, which they can do, there's a danger there where that passive filter can overload. So it's very difficult to extend the system, as it may need to be re-engineering. And we say typically ABB, passive filters are not normally recommended typically, and I'll explain why in the next slide or two. But we've got a couple of examples there in a diagram, nice little circuit diagram to show you what passive filter system looks like. And when we say, we don't normally recommend it, is that, passive filters can be in some cases difficult to design to operate in a system, as the system design has to be, you really need to know well about the system setup. And if, as I said before, that system changes at all, then the filter will not operate as designed. In some cases, those capacitors start to overheat, and in some cases have been known to set on fire, at least anyway. So yeah, there's a danger for resonance as well. You've got things like multiple branches required for filtering more than one harmonic. You also need a large space as well, and always provide capacitive power where AC drives do not require capacitive power, but generators may not cope as well with a leading power factor as well. Passive filters can never balance loads, so you need to have an accurate system design as well, but also you need to be aware of if anything changes in that network that you can cater for that as well. But in fairness, you do get a good level of harmonic, say clearance at least anyway, where your total harmonic distortion, can be something along the lines of that at least anyway. Another method, and this is a means of cancellation as well, is for having an active filter on the system where you have a means of reactive power compensation, harmonic mitigation, but also load balancing, and that power quality filter consists of, at least anyway. Nice little diagram there, just to give you a bit of an idea of what it consists of. But the best way to think of what an active filter is, it's a fully closed loop. Just think of an active filter as let's say, noise cancelling earphones. What an active filter does is very similar to what those noise cancelling earphones does. It detects some form of harmonics. It injects, let's say, the anti-phase of that to effectively cancel those out, so they have a low level harmonic content of your system, and you will get something as a result of that, along the lines of that, a very pretty good, I would say, fairly good smooth sine wave, at least anyway. You'll have some little notches on there, so you may have a harmonic distortion of the region of about 4 to 7% at least anyway. Another one is how we look at harmonics, and this is again driver related, so I do apologize because I wanted to generalize this about about harmonics in general. But there are, if we look at it from a drive's perspective, in some cases, instead of using a 6-pulse drive, you might want to use what we call a low harmonic drive that allows us to manage harmonics on a system. You may have heard the term things like active in-feed, active rectifier, active front end, or ultra low harmonic drive, and that's what they are. It's a low harmonic drive that manages harmonic content, and instead of having diodes on the input, you'll have IGBTs that switch on and off accordingly. They act as switches basically to control those levels of harmonics. Now, it has been said out there, and it has been known that some drives without the appropriate filtering can cause nuisance harmonics at higher orders, maybe above the 50th to the 100th order. But there are manufacturers out there, and this is ABB included, that will have a filter in their setup that eliminates the need of those harmonics at higher orders. So it's just a case, it's a very simple solution, this, where it's just 3 cables in, 3 cables out, and you don't really need to, and the harmonics is more, it's less of an afterthought, at least anyway, and you're not having to address things reactively and more proactively. But a typical waveform for that alone could be somewhere in the region of 3 to 5% total harmonic distortion. So comparing those mitigation methods, just to give you a bit of an idea, I'll just give you a moment or two just to read through those different sort of areas, things like ease of installation, things like power factor compensation. things like system efficiency as well, and redundancy as well. And that's quite an interesting one as well, where when we look at redundancy, depending on design, it may add cost as well, because if we look at probably an active filter in particular, you need to have a spare active filter typically on site, because if that active filter malfunctions, breaks down, it's out of action. And because that's being used to cancel out harmonics, your then harmonics could go back to high levels again, where high enough where it starts to cause problems on the system. So you need to have a spare available to be able to accommodate for that, at least anyway. But yeah, this is a nice little, let's say, takeaway to take from, where nice little checklist to say, if I'm looking for something that's quite easy, I could go for one option or a mixture of the two at least anyway. But when we look at the different mitigation techniques, the solution, and this is why I say it's not always a one-size-fits-all, it is dependent on various, several factors. Things like, what's the existing equipment that's out there? What's your footprint and volume? And the reason behind that is, if we're looking at an existing system, what have I got available to me if I need to do some form of harmonic mitigation? Have I got a lot of space? Have I got a very small space? But also, how easy and how much of a cost it will be in terms of installation and engineering, designing that system at least anyway. Is it a new installation or a retrofit? Understanding things like that, and also things like backup generators. Is it a temporary or permanent backup generator you've got there? And things like technology familiarity, as well as future proofing. And when we say future proofing, it's not more from a technology aspect. It's more, are there going to be any other new loads planned for that setup or system? But also the operational cost and the network characteristics are so important when we're looking at these mitigation techniques. As we come towards the end of our webinar session on an introduction to harmonics, there are some key takeaways, and hopefully by listening to this session, you've taken away probably 4 key things. Is appreciate what harmonics are, their source and the cause of them, the relevant regulations that apply as well. I always think system, it's all about the system, not just one component, unless you're a manufacturer maybe. An overview of the mitigation methods in comparison, but also it gives you a better understanding which solution is best for an installation. Again, it's not a one-size-fits-all operation. And on that note, I just want to say thank you very much for taking the time out of your lunchtime to listen to this webinar. I hope you found it very intuitive, very informative, but also enjoyable. And it's now over to yourselves now to see if there's any questions that you may have. So I'm just having a quick look on the comments or on the meeting chat, and there's none on there so far. So the floor is yours, at least anyway, if there are any questions.
Not a question as such, Liam. I just wanted to put it out there that this subject matter, whilst it's been around in the HVAC type industry for many years, certainly with the way that the industry has gone in the last sort of 10-15 years, with more and more electronic components getting into systems, this is becoming more and more of an issue, and certainly should be something that the designers and architects, consultants should be thinking more about. Absolutely. No, and in terms of installers too. No, along those lines. So yeah, thank you, Liam.
No problem. Thanks, Chris. It's really, really interesting point you made there, that we're getting to an age now where there's more and more electronic, components or products being put out there, which we've got to be aware of, definitely. So yeah, if there's any questions, please feel free to speak speak now or forever hold your peace at least. But don't worry, if you haven't got any questions, you're more than welcome to reach out to us after this session at least, and we'd be more than happy to have a chat about that at least anyway. So,
Any questions from anybody?
Yeah, Liam and Chris, Terry Sharp here. Firstly, thanks for your presentation and your input, Chris. And it's a very interesting topic. I think when we've been designing systems in controls and BMS for years, we've relied very much upon manufacturers complying with the appropriate standards, such that their equipment doesn't cause harmonics or cause injections of distortions onto the power side of buildings. Why has that changed now? What is the practical application that we need to consider on controls and BMS?
it's a very good question, Terry. Thank you very much for that. And yeah, I would say very, very good one. I'm just trying to think the best way to answer that now, at least anyway. But yeah, I think it's now become, I'd say, more important to be aware of it at least anyway. And if anything, it's just, I think it's become a historical thing where we probably see from our business the aftermath of it at least anyway, where equipment's been installed, and especially when we look at it from a drives perspective, is it's been installed and then maybe they've done some pre or post surveys at least, or done some assessments where they've had issues and they've said, oh, well, the drive's been installed, that's the cause of it. And then in some cases it might be, but in some cases it may not be as well, at least anyway. So it's becoming, I'd say it's starting to become more important at least anyway. And it all depends, again, when you go back to sort of G55, there's some guidance there, and it says, depending on how much you're adding onto the system, or if it's a new system, you need to be able to comply with that. And it's not to say that we won't support that. We will be more than happy to support that, and we also have tools as well that help with that as well, at least anyway. That definitely from a product perspective, we can give you things like what the typical harmonic content or levels are, at least anyway. So hopefully that's kind of answered your question. But if it isn't, we can pick some bits out of that and maybe go into a bit more detail at least anyway. So
yeah, I think that one of the key takeaways here is some of our members are in the aftermarket in maintenance and bordering on energy consultancy, and Harmonics is one of those inefficiencies that could cause overloading and penalty charges from the utility suppliers.
Yes.
So that's something that to very much be aware of. But I think this is a very specialist topic, isn't it, where ABB lead and others offer the monitoring services to identify and recommend solutions to those root causes.
Exactly. Very good point. Is not just ourselves. There's a number of companies out there that do power quality analysis and make recommendations on how to improve it. That at least anyway. So.
But great, something very much that we should be aware of. And so thanks for your time today.
No problem, Terry. Thank you.
No, absolutely, you're right, Terry. No, like I say, with the advent of technology and electronic equipment, absolutely that is the case. No, and yeah, maybe that's why it's changed. No, because when we just have faxes for argument's sake, because in an office situation, maybe it wasn't too needy, let's say, for a whole building. But now with mobile phones, computers, etc., then absolutely, yeah. Quite the point.
Yeah, much more noise being injected on the mains.
Yes.
Thanks for that question, Terry. Anybody else have any questions before we finish the webinar? No, we'll take it as silence as no questions, if that's okay. Liam, Chris, thank you ever so much for your time today and for delivering the webinar. We really appreciate it. Thank you to others who joined us. The recording will be available on the members platform probably tomorrow, and it will also be available on our YouTube channel, so you will be able to view it there as well. I will send the link out to those that registered to attend. But for now, thank you very much, Liam. Thank you, Chris, and thank you to everybody else for joining us.
That's great. Thank you, Catherine.
Likewise,
and
Catherine.
thank you,
Thanks for. Yeah. Sorry, Liam. I spoke over you then. Thank you, Catherine, for organising in the first place.
No problem at all. Thanks very much. Take care, everybody.
Thank you. Bye-bye.
Bye-bye all.
Bye.
Thank you, everyone. Bye-bye.